Class. Get my headset on here. Sorry about that. I am doing, I think, a very good lecture here on impulse and momentum, which is going to be close to the end of the lectures on dynamics. And then we're going to start to get into strength of materials. And I'll be sending you out reading material and stuff on that and everything else. But the last thing that I really wanted to do, and like I've said before, I would go through a lot of the derivations. I would love to go through a derivation on Coriolis acceleration, which is where as a thing is rotating, it's also moving out radially. And that produces Coriolis acceleration, which in space mechanics, of course, comes in very important, or you're not going to be at the right place when you want to be at Mars. Oh, I thought Mars would be here. Oh, but it's not. All right, so we've got two problems that I really think show this. What I've done up here is I've written impulse and momentum, energy, and equations of motion. Now, I'm not really even going to go back and start looking at the equations of motion, because more and more and more you're solving kinematic equations or kinetic equations, both linear and curvilinear, with energy analysis rather than equations of motion. And now what I'm going to teach you is I'm going to teach you that we can use impulse and momentum analysis exactly like we use energy, and we'll get the same answers. And even if we used equations of motion, in fact, we're going to use equations of motion. These are all tools. They don't work entirely separate from one another. I'd like to point that out, by the way, because I can write these equations, they play with one another so that you can use all these. These are tools in your engineer's toolbox, and you pull these out to solve problems with. That's what you're doing. You're solving problems, and you have to have a bunch of different tools to do that with. Now, let me tell you what we're doing, what we're looking at. We're going to look at a 10-story tall building. Here's my building, 10 stories tall. I don't know if that's 10, but it doesn't really have to be. Now, I'm going to throw a 10-kilogram shot put. Now, that's 22 pounds of shot put. It's going to go out the window, and it's going to, even see how I'm making my lines. I could be an artist. No, I couldn't be. That boat has sailed a long time ago. So what's going to happen, though, and I drew this wrong. I should have put that down. Well, actually, no, I can draw it there. It's going to hit an air conditioning vent. And so the distance that it is going to fall, right, is going to be 30 meters, because this is 10 floors. Let me just write this. 10 floors equals 30 meters. 3 meters per floor. So I've got 30 meters that I'm throwing this out the window, right? I hate it when that happens. When I'm walking along someone, all of a sudden I look up and there's a 22 pound shot put coming at my face. That would be horrible, wouldn't it? I mean, just please. Although I did read an article where a guy in Africa jumped out of a tall tree that he had been trapped in for 2 days by a lion. And he landed on the lion and broke the lion's back. I mean, I guess that's a good story, because the lion would have eaten him otherwise, and the lion probably still would have wanted to eat him. But I think it was the other way around. So it's going to hit this, and then it's going to indent this, right? So it's going to hit the air conditioner unit, and it's going to indent it. So it falls 30 meters. It indents the air conditioning vent 48 centimeters. So we have two events here, right? We've got this coming out the window and it's going down and it's going to hit the air conditioner vent. Then it's going to, the air conditioner vent is made out of aluminum, right? Aluminum, steel, whatever the cover is on, did I say air conditioner vent, air conditioning unit? So, you know, it's hitting it, whatever it's hitting, it's indenting it 48 centimeters. So we want to look at this in two ways, but we want to find a few things about it. We want to know what the final velocity of that shot put was just before it hit the air conditioning unit. And then we want to know what the average force was that it applied to the air conditioning unit, right? We also want to find out that the time that it took to stop in the air conditioning unit. We could also find out the time that it took to actually fall this distance, but that's just an equation of motion problem, really. So I'm not that concerned about that. But as far as the time to stop when it hits the thing, I mean, it's not going to instantaneously stop, is it? No, it's going to take a period of time to stop. It's not going to take long. You know, maybe a tenth of a second or half a second, or I don't know, a hundredth of a second. I actually do know. I'm staring right at the answer, but it doesn't matter. We've got to find that out. So those are the things that I want to find out, but I want to find them out in a couple different ways. I want to find them out using the equations of motion. I want to find them out using energy, kinetic energy. So let's do it using the equations of motion first. Did I turn that on? I sure did. Good. Okay, got him even on top of things. So if we do that, we're going to find out what the impact velocity. I'm going to actually write out impact, so you have it in your notes. The impact velocity is going to be, and we're going to use that composite equation that I derived earlier. Right from the two original equations that I really call the equations of motion. And of course, those are S sub F equals S sub O plus V0T plus 1/2 AT squared. And then the other one is just V final equals V. I'll write it V final equals V initial plus acceleration times time. So those are the two equations of motion that I'm talking about. And I used both of those, put those all together, and I came up with this equation of motion that we're using right here. So we know that the original velocity, I mean, I threw it out laterally. I just dropped it out of the balcony down onto that air conditioning unit so I could test my whole hypothesis out. Yep, it was 48 centimeters, all right. No, I'm kidding. Of course, I never did anything like that, except in my youth. So let's get back to this. So the velocity at impact is going to be 0 squared. I'll do that one. I'm not even going to put any units on it. So it's 2 times the acceleration, which is minus 9.81 meters per second squared. Sorry, I was just thinking about something there. Times the distance, which is 30 meters. This is what I was thinking about. I'm going to run out of room. And then I have to take that to the square root, right? So that doesn't look really good. That's 30 meters there, and I'm taking it to the square root. But the velocity at impact, right? I'm just going to write this out again real just 2, right, times minus 9.81 meters per second squared times 30 meters. the whole thing taken to the square root, and that gives me my velocity at impact, and my velocity at impact then is 24.25 meters per second. So let's keep that. We want to see that 24.25 meters per second is the velocity just as it hits the top. Just as it hits the top of that air conditioner. It's going 24.25 meters per second. Now, we could find out, you know, how long it took to get down there, whatever. I'm not interested in that at all. You know, let's also, though, let's analyze this a different way as well, because now that we've got the velocity at impact, we could just look at the deceleration, right? Because I've got the velocity at impact, and I know this fell 30 meters. Now, this fell 48 centimeters, right? So couldn't I use this same equation that I have here, except solve the equation now? So I've got V final squared minus V initial squared equals, wait a second. If I square that, I'll square that. That's V squared plus 2AS. So I've got 2AS over here. I want A, so I've got V final minus V initial. Yeah, it's getting late. Divided by 2S. And in fact, I probably just used that someplace here, but whatever. So if I did that, I know that my final velocity here is going to be V equals 0 meters per second, right? And when it hit here, it was just above that. So I've got 24.25 meters per second divided by 2 times 0.48 meters. And so I can use the equations of motion to figure out basically, you know, the deceleration that it's going to give me, 24.25 divided by 0.96. Equals 25.26. Wait, is that what I got? Oh, there's something wrong here. Just a second. Yeah, I thought you'd get me, but you didn't. I forgot to square that. It was only a second or so. Thank God I got off here. That's not what I have written down here, especially after, you know, that lecture that I had to just replace with a new one. Actually, the lecture that replaced it was much better than the one that was before it. And it was much shorter too. It was 10 minutes shorter because I knew what I was doing. And yes, I forgot. Oh my God! And there I forgot it on these, and that's why I didn't bring it through. So anyway, yes, I forgot to square that, and that is 612.56 meters per second squared. You know, that is over 60 G's. 60 G's is hitting that. You know, so we're using now, everything we've done so far is using the equations of motion to find out several different things, several characteristics about this incident with the 10 kilogram shot put that the track team from my rival school was doing up in the top floor there. So we know what the final velocity is. We've got that. The average force that we're going to have. Well, you know, the average force, we can just use this information that we've gotten, because doesn't that equal mass times acceleration, right? So the mass is 10 kilograms. The deceleration that we're going to have as it hits the top of this, I mean, you know, I'm just talking about the magnitude. We could say the deceleration, it's negative or whatever, but then we get a negative force, and we don't really, you know, whatever. Working against the thing coming down, I guess that's true. Don't worry so much about the direction of the force as the magnitude of this force, which is 6,125 newtons. That's quite a force. You know, how many newtons are there? There's 4.45 newtons in 1 pound, isn't there? That's right. You know, there's 745 watts in 1 horsepower. Right? Keep all of those conversion factors in your head. Those are the ones that, you know, I use most often and everything. Anyway, let's go back to this. So if we actually were to do that, then the 6125 newtons, if we were looking at it changing into a force, you know, a British gravitational force, that would be 1,376 pounds. So it'd be like we're walking up, and instead of, we put a 1,376 pound thing right on the top of there is what it would be like, right? Or if we wanted to get it in 627 kilograms. So here was the option. We can either throw a 10 kilogram shot put out and hit the thing on the top to get the insurance money. I'm joking, of course. Or we can find something that is 627 kilograms or 1,376 pounds and put it on there. How about a small car? You see the weight of something falling out that high, 30 meters. That's only 30 meters. That's only 90 feet high. And if something like that fell out of there, it would be disastrous. So now we've even found our average force, right? Can we find the time that it's going to take to stop? Sure. Right? Don't we know what the deceleration is? So it's going to hit here and it's going to end up here. So we know the velocity in the beginning and we know the velocity at the end. We know what the deceleration is now, 612.56 meters per second squared. So we can easily find out what the time is because we're just going to take the 24.25 meters per second and we're going to divide it by the deceleration of 612.5 meters per second squared. And that tells us how long, right? And what we're using this equation right here, right? And it's going to tell us how long. And in fact, what it is 0.03876 seconds, right? Or 38.76 milliseconds. Very quick. 3/100ths of a second, faster than you can blink. And isn't that our intuitive understanding that when a shot put is thrown out of a 10-story building and it hits a air conditioning unit by us, that it seems to be almost instantaneous? Well, it is instantaneous, literally, right? It's the blink of an eye. Well, actually, the blink of an eye is 1/100th. So it's 3 blinks of an eye, but you can't blink that fast. It'd be 3 people blinking in a row, almost 4. So there you go. That's the time that it would get there. Now, we've got a lot of information, don't we? We've got the time that it's going to take to stop. We know what the average force is. We know what the mass of the thing is. I should write that someplace. Mass is 10 kilograms. Of course, we've been using that for quite a while, so I think that you know, we all know someplace the mass was in there. Mass is 10 kilograms. I've been using that. And then we know what the velocity at the impact is too. So the way that we've analyzed this now is entirely analyzing it with equations of motion, right? I've got time to stop and all of that. What I want to do now is I want to look at impulse and momentum. What is impulse and momentum? Impulse and momentum. Impulse is F times delta t. And momentum is mass times velocity. Excuse me. Now, how do the units work out here? Well, let's see. Force is a kilogram meter per second squared, and time is a second. So that gives me a kilogram meter per second. And mass times velocity would be a kilogram meter per second. See how those work out and how F times delta T equals M times V? I have nothing to drink. Just a second. Let me just grab some water. Been a long day. Okay, I'm back. That was only a couple seconds anyway. I just grabbed my tea, which was sitting over on the counter. Now, let's look at this in another analysis with using impulse and momentum. What is our force? Let's just look at down here, right? We've got the thing. Here's my original air conditioning unit. The brick then is going to indent, did I say brick? The shot put is going to come down. It's going to indent this. We know what that distance is right there. It's 0.48 meters. We know the time that it takes. We know the average force. We know the time that it takes to indent that. We know the mass of the thing, and we also know the velocity right before it hit there. So let's see if this gives us the same information. You know, if we did an analysis of this, if we get exactly the same information that we got here, well, we know the force. Force is going to be 6125. So let's just check this. 6125 newtons. And we know the time that that force on it, you know, if that's an average force was applied, that would be 0.03876 seconds. And that should equal the mass, which is 10 kilograms, times the velocity, 24.25 meters per second. Wasn't that the velocity right before it hit? So I'm now turning my velocity into a force for a period of time. Here's my impulse. Here's my momentum. So this side's pretty easy. That's 242.5 kilogram meters per second. I'll write that. Right, even though it has no nickname. We got to give it a nickname. 24, that's a 4.5. Now, let's multiply out the other side. I already have, but I'm going to do it again in case I did make a mistake, and who knows. 0.6125 newtons times 0.03876 gives me 237.4. That's not exactly 242.5. Something has occurred here. I guess I didn't take enough units into consideration, or maybe it's calculator error. Let's see. What do I have here? 10. Yeah, that's easy. You know, I've used 4 there. So, but they're supposed to come. They're supposed to come. Or maybe I didn't. No, I used plenty of things there. And then mass times velocity. Maybe my velocity is a little bit off, but I don't see why. I use 9 point, actually it's 9.807, but that's not going to make that big of a difference, I don't think. Man, it must be the 6125. 6125.6. So it has a 6 there. So if I had kept the 0.6, I don't know if that would have done. That's not gonna. I don't think that's gonna do much. And then I kept all of those. So well, I'll try it. 6125.6 times 0.03876. No, still 237.4. So I don't know. There's something that's off here, but it's not much. Those are supposed to equate to each other, and I'm sure that's just calculate a round-off error in all of the equations that we've done. So you can see that force times the change in time equals mass times velocity. And we always have conservation of momentum, right? Now I want to look at this in one more way, and that is with an energy analysis of this problem as well. And we're going to probably do another problem very similar to this too, to do another impulse momentum, energy, and equation of motion so that you can see that we're really solving it, in all ways. First, I use the equation of motion to do this, but, I can use the energy method too. And so let's look at that. So right when it's about to hit the top, right, KE, right when it's about to hit the top is going to be 1/2 mass times velocity squared. So my kinetic energy is 1/2 times my 10 kilograms times my velocity, which is 24.25 meters per second squared. And that gives me, I left it off. I'm sorry. That's why I should read it to you when I'm doing it. 0.5 times 10 times 24.25. There you go. 121.25. Squared? No, just a second. 24.25 squared times 10 times 0.5. That's much better. 2940. And what is it? Joules. That's right. So we've got that, and we know what the energy is right when it's about to hit that. And we know that that has to be equal to the force times the distance that it indents, right? So if I take the average force that's being applied, which is 6125, and I take 2940, and I divide that by the 6125, that gives me 0.48, right? So D equals 2940 joules divided by F, which is 6125 newtons, and that gives me my distance, which just like before came out, either way we do it, we're going to get the same distance, 0.48 meters, right? I just want to show you that it doesn't matter which way you're analyzing this problem, you're still going to be able to find out, all of the information. Let me see what else. Okay, so we've got that. So yeah, if I, the next problem we're going to analyze more so with energy analysis, but then I'll also use impulse and momentum. So we can't really start off with impulse and momentum. All of these things being used together, though, give us a great understanding of the situation. And the more that we know about the situation, the kinetic energy that we've got here, the work energy on mashing that thing in, 48 centimeters, all of that. So I just wanted to point that out. Now, the next problem that we're going to be working on is we're going to be working on a bush pilot that is landing in Alaska. So now I've got a plane. The plane is landing. I'll draw the plane down here. Let's see. There's my top of my plane, and I'll put a little propeller on it, and there we go. There's the tail. Got some wings up there. I'll put some more down there. It's a biplane, I guess. I don't know. It is landing on here, and it's landing on skis. So the coefficient of static friction between the skis and the snow, right, for our Alaska bush pilot, I'll put Alaska, I'm regionalizing him, is going to be 0.2. We also know that the weight of the plane, right, the mass, or I should say the weight of the plane is going to be, and of course that's mg, is going to be equal to 1,000 pounds. I'll do this one in British gravitational unit. So we know that the weight is 1,000 pounds. We can easily find out what the mass is, because that would just be 1,000 pounds divided by 32.17 feet per second squared, right? And so that tells us that the mass is actually 31.06 slugs. Remember that, I don't know, you've probably seen slugs before, but if I'm the first one teaching you slugs, remember they exist. And remember you're dividing by 32.17. Don't ever forget 3.28 feet to a meter. Trying to get you guys to remember that. Now, when we look at this in a free body diagram, right? Let's look at it in a free body diagram. So we've got weight working down. I think everybody can still see the bottom there. There you go. Got weight working down, and we've got a normal force working up against the weight. We also have a frictional force, right? And that frictional force is working against the plane. The momentum of the plane is in that direction, but the force is working opposite to the plane, right? The frictional force is working opposite to the momentum of the plane. I'm not going to draw a force there because the plane is just slowing, right? Pilots turn the propeller off and everything. It's hit the ground. It's just slowing down now. So if mu sub s is, I should say mu sub k. Did I say mu sub s? Sorry, let me grab the pen there because it's landing. Mu sub s wouldn't apply at all. This is a kinetic coefficient of friction because the plane is moving, right? So that's my kinetic coefficient of friction is 0.2. And actually that's about realistic with skis, in snow. You go much further if you're landing in snow or whatever than you would if you're landing on a runway, really. Well, yeah, because you have no brakes. You have no brakes out here in bush country. I don't know. Have they invented a brake for skis? Maybe they have. But I've never heard of it. All right. So we have this, and what I want to do now that I've got the mass, I want to approach this using energy analysis. So we know that when this lands, it's going to have a certain energy, and that's 1/2 mv squared, right? So I know that it's 31 slugs. Oh, I forgot to tell you what the velocity was of the pilot landing. That is 70 miles per hour. So 70 miles per hour, right? We want to turn that into feet per second. So I've got 1 mile, 5280 feet times 1 hour, which is 3,600 seconds. So that gives me 102.667 feet per second, right? So now we know what his velocity was when he was coming in. We know what the mass of his plane is. So we can easily figure out what the kinetic energy is because we know the kinetic energy is 1/2 mv squared, isn't it? 1/2 mv squared. So let's just apply that. So 0.5 times the mass, which is 31.06 slugs, times the velocity, 102, oops, yeah, 0.667 squared. Am I squaring something? Yeah, squaring it, and that equals 163,693 joules, right? And so if we wanted to see how far it's going to take for him to stop, then we'd have to look at the force, the frictional force. And the frictional force, I think everybody can see, is just going to be 0.2 times 1,000 pounds, which gives me 200 pounds. So that's my frictional force. The distance then that it's going to take to stop. And notice I haven't used any impulse of momentum or any of my equations of motion to do any of this up to now, right? Okay, so we're just using energy analysis. And so I have 163 and divided by 200 pounds is going to give me 818 feet. So that's what it's going to take to stop that bush pilot when he lands on the tundra. If he's got a kinetic coefficient of friction of 0.2, it's going to be 818 feet. Now we can start using some other things, right, to find out the time, to show that the impulse and momentum are exactly the same. And that's what we're going to get to in the next lecture, because my alarm has already gone off. And I think this is the last lecture for the day. My voice is just about out. All right, see you at the next lecture, which will be a follow-up to this one, and we'll be, I think, finishing up dynamics. And then the lecture after that will probably be in solid mechanics.